Section 1.4 is on Euler's method. And Euler's method, we mentioned briefly in class, is a numeric way to approximate a solution curve for our differential equations. Now, one important fact or one important part of using Euler's method is we have to have an initial condition. So it is an initial value problem, but it's a numeric method or a numeric approach to approximating a solution curve for an initial value problem. So let's kind of, if you haven't already seen the lecture video, let's just look at a generic description of kind of how this works, and I'm not going to necessarily use all of these values, but let's suppose that we start out at a particular point. So we have an initial value, I'm going to call that x0, y0. And our differential equation, we're going to do first order Euler's method. So we have the slope. So if we know the slope at that point, then if we knew it was a straight line, then we could just draw a straight line with that given slope, and that would be our solution. But in most likelihood, our curve is not just a straight line. So that straight line is an approximation, but it's not a very good approximation. So what we're going to do is we're going to follow that straight line, but we're only going to follow it for a short period of time. If this were a time function. Here, it's a function of x and y. So we're going to follow that straight line for some delta x. They ask us to find approximate points for these various x values. And notice each of those have step sizes of 0.1. We often refer to those as h. And all that really is. So we're going to use this linear approximation, which is just using this initial value with the slope of the direction field at that point. And we're going to draw a line that scoots over this distance. And if we know this point and know the slope, then we can find this point. And with that point, we should be able to find the slope of the direction field there. And if we know the slope at that point, we can go over a certain distance. And each time, notice we're going over to the right the same amount. And if we know how far we go over and we know the slope, then we can find the next point. And we're just going to keep doing this. Whatever this point is, we should be able to find the slope, and that point we can go over, and then we're going to use that to approximate the next point. And we're just going to keep going until we do however many points we need. Now, of course, the smaller h is, the better approximation we would get, but that depends on how precise we need to be. So the question is going to be, okay, can I develop some kind of algorithm or something that if I know a point and the slope, I can get the next one? And there are several ways that we can go about describing this. Think about that the slope of a line is the difference in the y values over the difference in the x values. And if we get rid of the fraction, we can rewrite this as the slope times x2 minus x1 equals y2 minus y1. x2 minus x1, that's our h. M, that's our slope at that particular point. Now, in the generic form of the differential equation for this is dy over dx equals f of xy. So the derivative with respect to x is some function of x and y. So we evaluate our function at the first x and y, and that equals y2 minus y1. So this is the slope on the left side of our interval, this is the change in the x that will give us the change in the y. Well, if I know the y I started with, I can find the next y. So we're going to add y1 to both sides, and we would get y2 equals y1 plus f of x1 y1 times h. Or, I'm not sure which subscripts they use here, we could call this y1 equals y0 plus f of x0 y0 times h. Or we could write it like as a series, and we could call it y sub n plus 1 equals y sub n plus f of x sub n y sub n times h. So again, h is the change in the x, it's delta x. X sub n, y sub n, those are the current points that we're at. If we're going over a given x amount, we can find out what the next y value will be. So this is Euler's method. So this is what's known as Euler's method. So let's use that here. And let's try to evaluate this problem. That's not the one I was wanting. That's the one. Yes. Okay. So we want to use Euler's method to approximate our solutions for these different x values given this initial condition and given that differential equation. So let's just make a table of x's and y's. So our initial x value corresponds to y being 3. So we want to find out y when x is 0.1, 0.2, 0.3, 0.4, and 0.5. So our slope doesn't have x's and y's in it here. Let's write out our formula. So if we want to know the next y value, then we're going to take our current y value plus f of our current point times delta x, which is 0.1, and that'll give us our next y value. So if, remember f of x, y, that's just our dy dx. So if we substitute a 0 for x, well, there's nowhere we substitute a 3 for y, so we get 3 times 2 minus 3, so that 3 times negative 1. So we're going to have a slope of negative 3. At this point, at the point 0, 3, our slope is negative 3, and we have a delta x of 0.1. So if we do 3 plus negative 3 times 0.1, what's that? 3 minus 0.3, and that gives us 2.7. So that's our next point. So if from this point we move over 1/10 of a unit in the x direction with the slope given by our direction, it gets us to this point. And then we're just going to repeat this. So now we're going to say, okay, if we're starting at a y value of 2.7, well, when we're at this point where y is 2.7 and x is 0.1, our slope is our y value times 2 minus that y value. So that gives us a slope of 2.7 times, what's that, 2 minus 0.7, so negative 0.7. So negative 1.89 for our slope. And our delta x is staying the same. It's staying 0.1. So we just need to crunch those numbers. So that's 2.7. A positive times a negative will be a negative. This times 0.1 will be 0.189. So 2.7 minus 0.189 gets us to 2.511. So from the second point, using the slope at that second point, that would get us to the third point. And then we just keep going through this. So to get to the next point, we're currently at a y value of 2.511. Find the slope at that point by plugging that into the differential equation. So we have a y value of 2.511, and that's times 2 minus that y value. So let's see what we get for that. We get negative 1.28 times our delta x. So we're going to be doing 2.511 minus 0.128. That gets us to 2.383. And let's do that one more time. And we'll go ahead and do both of them. So now we're going to look for the next point. So our current y value is 2.383. Our slope at our current point comes from substituting into our differential equation. So our current slope is 2.383 times 2 minus 2.383. So a lot of calculator work here. So we get negative 0.913, and then our delta x is 0.1. So we end up with 2.383 minus 0.09. Let's just call that 0.091. I'm going to double check, make sure I typed that correctly. And yes. So 0.091. So we have 2.383 minus 0.091. 2.292. And one more. So to get from there to the next point, we're starting at a y value of 2.292. And we want to find out what would our next y value be. So that plus the slope at this point. So the slope of that point is given by 2.292 times 2 minus 2.292. So negative 0.669 times delta x. So 2.292 minus 0.067. If we go to 3 decimal places. .292 minus 0.067, 2.225. So this is our approximation through our first 5/10. So this can get monotonous. One thing that sometimes when you take MATLAB, if you've already had differential equations, and sometimes you'll write a program that'll have you do this actual calculation. You'll use a loop that goes through this, because all we're doing is we're putting a number, multiplying it by the slope, adding these things together, and repeating. We're just repeating a cycle where every time we're changing our initial y and our slope. Our initial y and our slope. And we're just going through a loop repetitively. So let's do one more example of this. So I actually changed this problem a little bit. I want to use dy dx or y prime to be 1 over x times 2y plus 4. They had a slightly different one, but let's use this one. Here our step size is going to be 0.2. H equals 0.2. We're starting with when x is 6, y is 1. And we're just going to go through this algorithm and fill in the corresponding y values. And they want us to go to 2 decimal places. So if we write out our algorithm, our recursive formula, now we just need to substitute. So our first point has a y value of 1. And if we want the slope at that first point, we put a 6 for x, and we put a 1 for y. So in parentheses, we get 6 over 6, so we get a slope of 1, and our h is 0.2. So we end up with 1 plus 0.2, so that gets us to 1.2. And then we go through this again. So to get to the next point, we're starting at a y value of 1.2. Our slope this time is 1 over our x value here. So our current x value is 6.2. Our current y value is 1.2. So in place of y, put a 1.2. And then we see what that makes. So again, our current point is 6.2, 1.2. We're going from there to get to the new point. So our current y is 1.2. To get our current slope, we substitute that x and that y into our formula that gives us slope. Our differential equation is solved for the slope. So put in for x 6.2, put in for y 1.2. So we get, let's see, 2 times 1.2 plus 4. That's divided by 6.2. So I'm going to keep a couple of extra decimal places intermediately. So 1.032. 1.032. H is 0.2. So we're going to take that answer we just got times 0.02, and then we're going to add 1.2, add what's out front. Into that I get 1.22. 1.22. And then we just continue doing the same thing. So to get to the new point, our current point is 6.4, 1.22. So to get our new y, it's our current y plus the slope at this point. So our slope is over 6.4, 2 times our y plus 4. So our slope, let's see, run that through our calculator. 1.00625, and that's times our delta x. So when we do that, I get that. Type that in wrong. 1.00625 times 0.2 plus 1.22. To 2 decimals, that's 1.42. So when x is 6.6, we should be at a height of 1.42. So we're going to use that point to get our last one. We want to find out when we get to 6.8, what y value are we going to be at? So we're starting at a y value of 1.42. Our slope at that point is y prime equals 1 over that times 2 times the y value plus 4. So our slope, we can type that in. I get about 1.0363 repeating. That's times 0.2. And then we add the 1.42 out front. So 1.63 to 2 decimals. So we're just crunching a lot of numbers, but it all goes back to this formula, known as Euler's method. So you could imagine we can make a plot out of this, and this would give us a plot that approximates what our solution curve would look like at our initial condition, the initial value of our differential equation, and then we plot over a known step size with the defined slope that we're given from our differential equation.